We want to continue where we left off in our last video by looking at Desmos. You can see here how the data that I've put in Desmos already is the same as the data that we have from our helicopter dropping a package. So, you got 0, 1 second, 2 seconds, 3 seconds, 4 seconds all go in the X1 column, and the 350, 335, 283, etc. go in the Y1 column. So now what we want to do is a quadratic regression equation. So a quadratic regression equation is going to start off by using y1, and then we hit the little tilde in the upper left-hand corner of your keyboard. And then we have an a times x1, and we want to square that. So I hit the little a squared button there, and it just squares it, plus bx1 plus c. And now what we have is the quadratic regression equation, where you can actually see the r squared value, which kind of tells you how good of a fit the model is, which 0.99 is a really good fit because if it's close to 1, that means it fits perfectly. You can see down here with the parameters, this is the a value, negative 15.3571. The b value is negative 2.27143, and the c value is 350.686. So those are the numbers that you would replace the a, b, and c with in this quadratic regression model. So if we go back to our problem here, would a quadratic function be a good model for the data? Yes, it would be, because we did a quadratic regression model, and you can see how well the quadratic equation fits by looking at the graph. So you can see how the curve of the graph here is looking like it's going through most of those points. Another way to determine that is by doing the residual, which you see the residual here, this E1. So if I go up into my table, and you can see an E1 here, you can see some residual values, like you got a couple of them that are negative, a couple of them that are positive. If I wanted to graph that, I'm just going to click on this button up here. So my residuals are actually going to come up in black, which you can see some like black stuff down here. If I expand this, or if I enlarge that, you can see how you have some dots above and below the x-axis. So when I look at the residual, that's how I can tell that I have a good fit, because I have some above and some below the x-axis. So if I were going to answer this question, would a quadratic function be a good model for the data? Yes. And the reason being is because the residual points are above and below the x-axis. In other words, some are positive and some are negative. So that's really what you're looking for, some positive and some negatives, to determine if the residual, if the quadratic regression is a good fit by looking at its residual. Now, if I go back to this quadratic function here, there is actually another way I could type this in and still get the regression curve. So if I were to type it in, see what I did up here is standard form. I can also type it in vertex form, which is y1 tilde, still have an a, but now we're going to have a parentheses x1 minus h, close the parentheses off, square that, and then plus k, and once again, we have a new equation, which you can see the line, and you have an orange line and a purple line. They're the exact same line. So you see the exact same line here over top. which is both the orange and a purple, because they are the same equation. It's just one is in standard form. The orange one should be in standard form, and the purple one should be in vertex form. And then you can see it has the same residual, or the same R factor, which should have the same residuals, right? They still have the same residuals. But now you have the A value, which is actually the same, an H value and a K value. So you have the vertex is near 0 and 350. So the vertex is near that point. So very close. Let's take a look at the next question here. So a company offers rectangular pool sizes with dimensions as shown. Each pool includes a deck around it. If Carolina wants a 15-foot wide pool with a deck, how many square feet will she need to have available in her yard? So the first thing we want to do is write a quadratic function that represents the area of the pool and the deck. So you can see the pool has a width of x feet and a length of 2x. But we want the pool and the deck. So the deck is an extended 4 feet on each side. So the deck with the pool would have a width of x plus 8, because 4 plus 4 is 8. And the 2x is also extended 4 feet on each side here and here. Right? So the length of the pool is 2x plus 8. So the length of the pool with the deck attached. So we want to write a quadratic function that represents the area of the pool and the deck. So you just do the area of a rectangle, which is length times width, and that's going to give you 2x plus 8 times x plus 8. So that's your quadratic function. Now maybe you want that in standard form, so you would take that and use the distributive property to multiply it. So you would distribute the 2x to the x and get 2x squared, distribute the 2x to the 8 and get 16x, distribute the 8 to the x and get 8x, and the 8 to the 8 and get 64. And then you go one step farther, and you would get the area equals the quadratic function 2x squared plus 24x plus 64. So that would be your quadratic function in standard form. What is the area of the pool and the deck? Well, if we know up here Carolina wants a 15-foot wide pool, we would know that the x here is 15 feet. So all we have to do is plug in 15 for x. So we can plug 15 into this green equation, or we can plug that 15 into the red equation. Either one, it doesn't matter. It would still give us the same answer. I'm going to pick the red equation. So 2 times 15 plus 8, and then 15 plus 8 in the other equation. So I'd have to do 2 times 15, which is 30, plus 8, and 15 plus 8 here. Now I do the parentheses. 30 plus 8 is 38, and 15 plus 8 is 23. So now I just need to do 38 times 23, and that gives me 874. So the area of the pool is 874 feet squared. Because anytime we do area, the units are always squared. And one more question here. Let's take a look at this. Each year for the past 5 years, ticket prices for a school play have increased $1. So you can see the ticket prices here. They've all gone up $1. The director used this function, f of x equals negative 7x squared plus 90x plus 750, to represent the relationship, kind of like a quadratic regression model for the number of prices. How well does this data represent? Well, it gives you the predicted value, it gives you the actual. So here's your actual. Here is your predicted. So all you have to do is subtract. So 745 minus 750 is negative 5. And then we subtract there, and you get 13. And then we keep doing this. And what we're looking for